So today we're going to talk about gas law stoichiometry. And we're going to do stoichiometry using PV equals nRT. And before we do that, I'm going to update, you know how I've always kind of talked about my roadmap, which is that the central unit in chemistry is what? Yeah, how many moles? And that if we know that, it provides us with other information. So if I know how many moles I have, what's another piece of information I could get? I could know how many grams I have. All I need to know to do that is what? I just need the information on the periodic table. I need atomic masses. I could figure out how many liters I have of the thing. What do I need for that? Yeah, I just need my concentration in moles per liter, right? I'll say here periodic table. And we said once I know that, I can figure out how many moles of some other thing, right? And all I need for that is the equation. And of course, once I'm there, well, then I can figure grams out for something else. And I could also figure out how many liters of something else. So I have so much power, right? Tons of options there. But now we have another piece of information, which is we could figure out either pressure or volume or temperature, right? And what do I need to do that? Well, I know that PV equals nRT. Pressure times volume will be equal to the number of moles times T. What's R?
R is placeholder?
It's constant, the ideal gas constant, right? And of course, from this top one, I could also go there, but we'll keep it simple. So if I'm doing stoichiometry, the question could say, hey, if I start with this many grams of carbon, if I burn it in a sealed container, what will the pressure be at the end? Does that make sense? Well, you know, if I burn carbon, what's the gas I make going to be? So I can figure out from how many grams of carbon I have, how many moles of carbon I have. From how many moles of carbon I have, I can figure out how many moles of carbon dioxide I'll make. And from how many moles of carbon dioxide I make, I can then find the pressure as long as I know volume and temperature. Does that make sense? Is that bad?
Yes.
It's just the stoichiometry you've always done. In fact, the stoichiometry you've always done even easier, because normally the question would say how many grams of this stuff or how many liters. But for this, you're going to stop at moles. You'll get your answer. You'll know how many moles of carbon dioxide you have. And then you will just use PV equals nRT. Does that feel reasonably comfortable? All right, let's try a couple. Let's see how that goes. So this question includes needing to know what standard temperature and pressure is. Can somebody remind me what standard temperature and pressure is?
0 degrees Celsius.
Good, and if it's 0 degrees Celsius, how should we report that?
273.15 Kelvin.
Very good. And what will the pressure be?
1 atmosphere or 101.3.
That's right. And I prefer to work in kilopascals, though it is certainly not wrong to work in atmospheres. But, you know, I'm the guy with the magic pen, so you're going to work in my unit. Ha ha. Oh, yeah. All right. So keep in mind, when it says how many liters of water, are we talking about how many liters of liquid water here? Would I use a graduated cylinder to measure this?
Yes.
Really? Why don't you look at this equation? Look carefully at it. What do we notice? What is this equation? What are we? Yeah, we are making gaseous water. Because what is this actual reaction? Boom, sure. Boom or flame, depending on how we set it up. But we are taking hydrogen gas and we are reacting with oxygen, which we typically call burning it. Good, yeah, combustion. So we are doing the combustion of hydrogen, which will give us water, but that's pretty hot. So it's not giving us liquid water, it is giving us gaseous water. Good. So if we think of like that roadmap approach, really, we know that we are starting with 5 liters of oxygen gas. Now, to do this, going over here, in fact, I might have to show this here too. P V, T, same thing. So here, we are starting with knowing how much oxygen gas we have, right? We're starting with how much oxygen gas? 5 liters. Okay. So we are starting off with a volume of oxygen gas. What are we going to figure out from that? How many moles of oxygen gas we have? What equation or what information will we use to make that happen? From volume to moles, it's a gas.
Avocados.
That would be for a change. In this case, the ideal gas law. Does that make sense? We're going to have to use PV equals nRT. That's how you go from here to there. Then this is easy. From moles of oxygen, we're going to figure out moles of water. That's easy. All we need is the equation, which we have here. Looking at it really quickly, if I use 1 mole of oxygen, how many moles of water will I get?
2.
2. All right. And then I need to know how many liters of oxygen. How will I do that? And to do that, I'm going to use... And so this is worth keeping in mind. This is liquid, right? And this is gas. Does that make sense? This is actually, not only is this a liquid, this is really what I should say, this is aqueous, right? Here we're talking about a solution.
Right, volume can also be like the volume.
That's one and the same thing. A gas will always fill the volume of its container. Yeah, so this means you're collecting it in something that's volume can change, most likely a balloon, which we do, right? Like we collect gases in a container like that, or you could be collecting it in a collection jar that displaces water. That's a common way we do it. But we're collecting it in some way where we can control the pressure and temperature, but the volume is what's changing. The most common thing for that is, have you guys seen a gas collection jar before? Can I show you?
Yes.
A gas collection jar, and we have trays for them in the back, which I won't get right now. But a gas collection jar just looks like this. And we have a tray it sits on. You fill the tray with water, and you fill the jar with water. Should I go get a tray? I don't have time.
Yes.
No. If time permits, you'll do a lab like this on Tuesday, so you'll be good. In fact, you'll do it with graduated cylinders so you can track the volume. But look here, all you do is, this container is not big enough, but that's okay. That did not go well. That didn't go well at all. All right, let's. This is going to be a mess, but that's okay. So for a gas collection jar, you would just see how that has liquid and gas in it?
Yeah.
You have a tray that allows you to run a tube underneath it, and you just run a tube into it. You connect that to your test tube or your flask or whatever you're doing the reaction, and you seal it so that as a gas is produced, it goes down the tube into the jar. As it goes into the jar, the gas is a lot lighter than water, so it's going to float to the top. And what does it do with the water that's in there?
It displaces it.
It pushes it down, displaces it. The nice thing is the pressure is pretty consistently 1 atmosphere, right? Because it's pushing against 1 atmosphere up here. So you can control the pressure in there. Nice. And the temperature you can measure. You can keep a thermometer on, right? And so knowing that, you can know exactly how many moles of gas you have in there using PV equals nRT.
And then ideally you would have as little air in there as possible.
When you set up with this is a stupid thing to put this in.
Yeah.
The trays are wide, so it's easy to put it in and then make it go upright. So there's no air in it.
So is it not at all? Perfect.
Yeah, I mean, cool. Might be some, but if you do it properly, the'll be none.
Approximately not.
Does that make sense? Hi guys, how you doing? Your assignments are over there. Where did I put my pen? There's my pen. All right. So let me ask you really quickly. For this question, how many times are we going to do PV equals nRT?
A lot.
Twice.
Oh.
Or, that's one approach. The other approach is you could do this using Avogadro's law, because the number of moles change, right? So you could figure out how many moles you start with and how many moles you end with and do Avogadro's law. I don't think that's meaningfully quicker, but you could do that.
That's the same. Or...
But either or, both work. So let's approach this. Shall we do the first one just together, and then I'll set you loose after that? All right. So the first thing we need to do is go from liters of oxygen to moles of oxygen. And I know that to do that, I am going to be using the ideal gas law. So let's set it up. So it's kind of useful, since we know we're going to have 3 steps, I'm going to kind of set this up here, and we'll say PVNRT. And we know that number of moles is what we're looking for. What is the pressure? Kilopascals, yep. What's the volume of this gas? We have 5 liters of oxygen. What is the ideal gas constant? Well, we don't know that till we know what our temperature is. What's our temperature?
273.15 Kelvin.
Okay, so we need an ideal gas law that's kilopascals, liters, Kelvin, and we want moles. That is, does anyone remember it? 8.314 liters, kilopascals per Kelvin mole. Good. Does that make sense? I know I mentioned it in the video, but okay, I'll get after. I want to mention again how important it is to make sure that you're using an ideal gas constant whose units match the units you're using. Even though it's an equation, really it's a form of dimensional analysis you're doing, and it only makes sense if the units cancel, right? So then we're solving for n. What is the ideal gas law for solving for n? PV equals nRT, so n equals PV over RT. So that equals 101.3. And I'm going to not put units in here just for space. We know they're in there. We know they cancel, right? I can't do it. Yeah, I can't bring myself to do it. What's our volume?
5 liters.
5 liters. R is 8.314. I thought I had a finer pen. I was wrong. And what's our temperature? All right. So there we go. And can someone do that math for me? We should be talking 2 divided by 8, so we should be talking roughly 0.25. It'll be a little less than that, 0.1, like between 0.18 and 0.2 something.
0.223.
There we go. All right. 0.223.
Yep.
Now, I'd like to point out this is actually more significant digits than we really have to work with, isn't it? But because we're mid-question, hang on. All right? We will do our rounding at the end. So we know now how much oxygen we have. Do those steps make sense? PV equals nRT. Not a big deal, right? Now we're going to do the tiniest, littlest bit of stoichiometry imaginable. We're just going to say, if we have this much oxygen, how much water will I get? Does that make sense? We're just making this step right here. That is the shortest little dimensional analysis you'll ever do. So we know we have 0.223 moles of O2. And we're just going to say, I don't want to talk about moles of O2. I want to talk about moles of... And what is that ratio?
1 to 2.
Which one's 1? Which one's 2?
O2 is 1, H2O is 2.
Awesome. And that should then give us, obviously, 0. What? Huh? I'm going to write this below. Are you still doing the upside down calculator trick? Because if I can give you a pro tip, don't do it when you're trying to get numbers. It's all good when you're trying to spell eggshell.
0.4.
Less good when, you're trying to get math done. And see how for organization's sake I'm kind of organizing my sections here? That's not a must do, but it's kind of nice. And now, what's my last step? I went from knowing how many moles of
H2O.
oxygen I need.
Moles of H2O.
By the way, you can do all of this with dimensional analysis. You could just start like this and then keep going and do it in one big dimensional analysis train. I've seen students do that, and it's great, and it works wonderfully. So really, you get a big PV equals nRT fraction, then you'd multiply by this fraction, then you'd do another big PV equals nRT fraction. That works great. It's not what I'm going to teach you, but I've seen students do it, and they love it. So keep that in mind. If that's something you want to fiddle with and see if that suits you, great. It's not what I'm going to do. But it does work well. To be honest, it's what I do when I'm doing a question on my own. I find it a little confusing to teach. If you found what I was just saying confusing, ignore it completely.
What?
Moving on. I'm just saying you can do this as one big long line. You can do it as one big fraction. And it actually works quite easily. It's not a terrible thing.
Okay, I can try that.
Anyway, but I'm not saying you have to. Just some people like it. Okay, now I know how many moles of water I have. What's the last step? It's this one. So what do I need to do? What do I need to do? PV equals nRT, right? So no problem. P equals V equals N equals R equals T equals. The truth is, what's the only one of these that's changed? V's our question mark. We know N. What's N? Yeah, 0.446. What is R is still 8.314. Temperature is still 273.15. Pressure is still 101.3. Right? See? See?
This was the best part of chemistry.
It really was.
Oh, I'm so good at that. Or I was when I was your age.
Hey, what is the ideal gas law if you're solving for V?
It's the same. V equals
nRT divided by P. Cool. And that would then give us 0.446. No, but she is here. I can't remember where she told me she was working. But she's...
That's useless to me, young man.
Perhaps the library?
Thanks, you're beautiful.
She was snarky, I remember that.
You want me to be snarky too?
No, it's all good. I feel like I've had my fill.
You're beautiful.
Right? And down here for pressure, I should put 101.3. I am going to exclude my units there because I could have made this space a little bigger. And we're going to get cool. Now, the keen amongst you will note that there's lots of shortcuts to do this an easier way. There are a lot of shortcuts to do this an easier way. I'm not going to teach them to you because I don't want to confuse you. But if you're spotting and saying things like, wait a minute, couldn't I have just? The answer is probably yes, you could have just. But better to learn it the full complicated way and then find shortcuts as you go. I'm a firm believer in. Yeah, yes. I'm doing it this way because you'll get to some questions where I start you with mass and you can't, but yes, this you could have absolutely, you absolutely could have. This next one you can't. So I want you guys to try this one, and what I'm going to leave you actually, is it fair if you guys look at the question and I'm going to leave this up here so you can kind of help do some planning. All right, so take a minute, see if you can figure out how we want to approach this question.
Do you know what's going on?
We are finding out typically the day before things actually happen. So I don't know anything more than you guys know.
Is there any more? It was on the news. We were like talking about it.
Yeah, so I know I found out yesterday we're not doing EQAO. So,
Oh wait, really?
Yeah, so not that.
on the news.
But sorry?
On the news, you said?
No, we found out a little sooner. We got an email in the morning. But yeah, we find things out as they come. So yeah, I don't think about it. I'm hoping that we aren't missing many days of class because I find that frustrating. Other than that, they want me to stand outside, I'll stand outside. They want me to hold a sign, I'm proud to hold a sign. But I don't like missing class. Yes, sir. Yeah, let me come take a look while these guys give this one a shot. It's hexane, but that's obviously not a single bond there. That is a
Double.
I don't see two. I see triple. It's a triple bond, so you have to name it accordingly.
Oh, hold on. 1 second. E.
Yeah. R? Okay, it's not something you figure out, it'll be given to you. The only thing is there's a bunch of R's, because you have those different units for pressure. There's a different R for every unit of pressure. There's a but they'll all be given. You do not have to know anything like the formula sheet, and it will say R like this for kilopascal, right next to it. There's like a front one that has atmospheres, right next to that R that has torque. You don't have to have those. Alright? Let's try this one. See what you got. Yeah.
So, is this just like over the base? Is it just this number again?
Yeah, so whenever it's STP, that's called standard temperature and pressure. And by definition, standard temperature is 273.15 K, Celsius, the freezing point, and 101.3 kilopascals. We use this as standard because this temperature is super easy to get. I just do the reaction like, if I mix ice and water and stick my test tube in there, then I know its temperature is going to be 273.15. So nice and easy. And then this is just like normal air pressure. Like right now would be, in a lab, we have a fan in place to control it more exactly. But at any given day in Ontario, it's going to be between like 90 and 100 hours. Like it's in that range.
And then for the volume, is that once you fully convert?
Well, so in this case, the ENRP is probably going to be the last thing. That's okay, still set it up. You're going to need N. You're going to have to know how many moles of hydrogen you have. And to get that, you're going to have to work with the 55 grams of oxygen gas.
So I use this. And then
In stoichiometry, you just get to how many moles of hydrogen, and then you can throw that in this. So this, it's fine, leave it here. This will actually be the second step. Your first step over here will be stoic. That's right. So it's an alkyne. That's right. Yeah, there's 4. So it'll be a butane, and then you. What? Coming right up. I'll be done. Yeah. I like everything except hex implies 6 carbons to me, but how many carbons we have there? That's a triple bond, but it doesn't give you extra carbons. There's 1, 2, 3, 4. Yep. Yep, I even numbered them for you. It's trying to be nice. Trying to be nice. No. Triple bond. So you have not this note, but this one. That page will be all over
Be a 1-1 ratio, right? Just two partially equal. Be a 1-1 ratio.
Yep, 1-1 ratio. From hydrogen gas, of oxygen gas. No. From oxygen gas to water. 2-1, or 1-2 ratio. 1-2 ratio. Right? From oxygen gas to water gas.
I don't think there's one more here, right? Right?
Yeah, so it's a 1-2 ratio.
Okay.
Yep, 1-2.
What?
Yep.
So for the stoichiometry, since it's practically telling you
How many
volumes
volumes
of water temperature.
So the volume is what we're looking for, right? We're not looking for N. The question is how many liters of water? And it's a gas, right? Like, I know we think of liters of water as being like a liquid, but water here is a gas. So how many liters? That's what we're looking for. So that's your question mark. Which means this isn't actually going to be step 2. This is actually for the step 1. This is actually going to be step 2. That's okay. We'll leave it right there. Because you need N. First you need to know how many moles of water you get. And then once you know that, then you can do your PV equals nRT. So let's take a look here. We're starting with grams of oxygen. So we're going to go from grams of oxygen to got to be the same thing, right? So got to be moles of oxygen. And then eventually we want to know how many liters of water. So we'll go from grams of oxygen to moles of oxygen to Well, we want liters of water, so we got to get to liters of water. So to get to liters of water, we have to stop through moles of. Yeah, that's right. So we'll go from grams of oxygen to moles of oxygen to moles of water. Then we'll stop. We'll get an answer, because then we're going to use PV equals nRT. And the moles of water we get here is what we will put in number of moles. Does that make sense?
Yeah.
Awesome.
That actually does make sense.
Isn't that helpful? I find that so helpful.
So just solve for moles of water and then plug it into the formula.
Yeah, no, this does make sense.
How are we feeling?
Now, we have the number of moles, so we just multiply in
Not really knowing is a two-step.
that and multiply in the temperature.
So,
Then divided by.
grams don't go to liters.
Yeah, no.
Oh, that doesn't make sense.
The trick
So we
is,
just do this entire big calculation.
so this is actually the question. This is a question mark right now. We're actually going to need to put a number there. So what we're going to do is then, if you go back, let's say we're going to that equals 1 gram. So you can always go from 1 something wrong, 1 to next. So that's the equation. We're going to go to grams. I don't know how to do that. You can go to grams, all we need to figure out.
77. Yeah. And it's down to 66.
Why do you have 2 moles? Yeah, so it should be 5 grams. 1 mole. It should be 2 moles.
No, it's one, right, it's oxygen gas and then it says hydrogen, which means it's gaseous.
0.08.
Oh,
Right?
shoot. No, no, it's an R. Then R answer.
Or you can just convert the atmosphere to kilopascals.
Yeah, it would be
By doing a simple
So in this question,
You
you
got
have
chlorine
grams
gas.
of oxygen.
You
You
can
start
just
with grams of oxygen.
So
And eventually it wants to know how many liters of water is right?
I understand this number.
So it should be 1 mole.
We want to get to liters of something else.
Look, it even shows you really
So what's what happens?
Yeah.
This number is right.
Remember, constant volume.
And I gotta get to liters of water.
So this is what he did. This is the H3.
Figure out how many grams of oxygen I have, how many.
You can just make it. I
Then I'm going
figured it
to
out.
use that as how many moles of terrible. Water, I think? Yeah. So yeah, grams of oxygen, moles of oxygen to moles of water. And then we'll stop, because now we'll have N. That's our N value.
Pressure.
And then we'll use P.
That was on the
That is our N. Does that make sense?
Yeah.
Actually, really simple structure, like easier stoichiometry so far. And then, PV equals nRT, bam. Does that make sense? Oh, come on.
Go right to the end.
I know you love drawing pictures, so it's your turn to draw me a picture, kid. Alright. So it tells me how long is the main chain.
How many layers are trying to unfold?
How long is a chain that is a
grams, which we just did.
How many parts?
I got 7706 with the same.
Yeah.
Which is fine.
Probably.
5 grams of oxygen.
Oh, he did it wrong.
R.
Love it. Okay, so make me change my
No, no, it's not even that. He used the wrong one. I don't know why he's using moles of oxygen. That's
Love
what
it.
he
One, two. And then it says that E means that there is a, and we do the double bond starting at carbon.
Because I used all this.
Oh, no, it's
No,
because,
no,
yeah, you did that.
to show
and then
the
you put
double
that
bond?
instead of having carbon.
Yes.
What? Mechanical pencil.
Okay, so how many liters of water?
So just start at 1. So it tells you the number, and start at 1. That's it.
Right, this is basically the other
Bam.
question.
Bam.
Basically the previous question, but with, yeah, specific pressure.
Nope.
So it's
I'm coming. Yeah.
It's trying
What you're running into here is that you're trying to do P equals NRT first. But actually, you can do P equals NRT last. If you look at this, you're starting at knowing how many grams of oxygen you have. And you want to know how many liters of water you get. So tell me what your steps are. So grams of oxygen, so moles of oxygen. That's the only thing I can do, right? And then we don't actually care about oxygen, so then we're going to do moles of
the Aussies are on fire.
and then we can go to, and where's the PV equals NRT in this step? Do we do it first? No, we do it here. So you're going to do this, stop, step number, then you'll do PV equals NRT, and then you'll does that make sense? Do you want me to give you a couple minutes to do that, or do you want to go through it with me and then they'll feel like you've seen it? Okay. Hey guys, is it okay if I go through this now, or do you guys want a couple minutes more to try? Like, please go. Okay, let's talk. All right. So the trick with a question like this, I think, is to map it out. So if you look at this question, we start with 55 grams of oxygen, and it says, how many liters of H2O gas, right? Does that make sense? That's the question. Can we all see that? Did I put a few other things in there? Sure. But the basic question is, with this much oxygen, how much water can you make, right? Okay, so let's look. We are starting with a mass. So look here. I am starting with a mass of one thing. And I want to get to how many liters, the volume of another thing. So let's look at that. It means I'm starting here, and I want to end up here. Can everyone see that? So how do I do that? Well, to go here, first I'm going to know how many grams of oxygen I have. Then I'm going to know how many moles of what? Moles of oxygen. Then I'm going to know how many moles of water. Then I will figure out how many liters of water, the volume. Does that make sense? So guys, when will I stop doing dimensional analysis here so I can start doing PV equals NRT? Well, this is dimensional analysis. This is dimensional analysis. And then I'm going to stop. I'm going to take that number, and I'm going to use PV equals NRT. Does that make sense? All right, now we've drawn it out. Let's do it. So we're going to start with a little bit of dA, and we're going to go from grams of oxygen to moles of oxygen to moles of water. And it doesn't hurt to kind of draw it out for yourself like that, right? Be like, okay, I know what I'm doing now. So now let's do it. I had 55 grams of O2. But I don't want grams. What do I want? Good. So what should I put where? Good. And off the top of our head, do we know what a mole of O2 weighs? 32.0, right? Does that make sense? Where did I get that information? Now the periodic table says 16. Why did I put 32?
Yeah, 2 grams of oxygen.
Yeah, it's O2. Right, good. Okay, what units cancel here? Grams of O2. If I stopped calculating right now, what would I know? Yeah, how many moles of O2? Does that make sense? Now, I don't want moles of O2. What do I want? Moles of H2O. What's that ratio? What's the ratio? Yeah, I think so. Yep. Like that, right? Okay, that's going to be 110 divided by 32, which means it's going to be 3 point something. 3 point what? Somebody got this for me? .44? Nice. I swear I used to be a lot better at the mental math. I used to always get the second decimal. And somewhere along the line, maybe I've just stopped trying. Okay, now let me ask you, this is not the answer to my question. Why did I stop? I stopped because what am I now ready to do? PV equals nRT because now I know N. Now I know how many moles I have. So now we can set that up. So this is kind of like all our step 1. And now our step 2 is going to be, okay, PV nRT. Is this still at STP, this question? Are we still at standard temperature and pressure? So pressure then will be what? 101.3 kilopascals. Volume is what we're finding, right? What's our number of moles? Good, I love it. What's R in this case? What is R in this case? 8.314 liters kilopascals per Kelvin mole. And temperature, it's standard temperature, which is what? Hey, by the way, I mentioned this over there, but why do we, look here, this is a question for everybody. So pause from what you're doing, even if you're deep in something. Because I want to ask, why do we use that in the lab as our standard temperature? What makes that a really convenient temperature to make our standard temperature? It's freezing point. That's 0 Celsius, right? Why is that such a convenient number? Why do we like that? Like, why make that standard? Because that's cold. Like, if I'm a scientist, I don't want to be in a... So what, I have to go in a freezer every time I want to do chemistry if I want to use standard temperature and pressure? Why is that the standard?
We can throw ice and water and put the vessel in it.
Does that make sense? If you are doing chemistry in a test tube, you're collecting gas, and I told you we have those wet trays where we collect gas. If you want to collect gas and make sure that you are controlling the temperature is actually really hard to do normally, right? Goodness knows this if you've ever lived with somebody else who has a different feeling about what the thermostat should be at than you, right? They change it and then it takes what feels like hours for it to come back. Oh, I'm sensing tension. Is there tension here? Do we have a difference of opinion of what makes a comfortable room?
72.
Not us.
No, not you.
We're usually on the same page.
Is it, yeah. Because I will say at home, I am turning into my grandfather. And when anyone turns it above like 17 degrees, I'm like, oh, I see money grows on trees then. And then I raise like a big, oh, go. Are you going to pay the gas bill? Is that the plan here? And then I turn it right back down. And we have a lot of fights. There's a lot of fighting with my children and I about the temperature. So I relate. Anyway.
They say it's too cold or too warm?
Too cold. I keep it pretty cold. So the temperature is normally hard to control, but a really easy temperature to control is ice and water. Because if you have ice and water and you let them sit for a minute and come to control, they will sit at 0. And as long as you're not pumping tons of heat into them, that ice will absorb the heat, melt a little, and keep it at 0. And as long as you keep adding ice, you maintain a constant temperature. That's why that's our standard, because it's easy to work with. It's really hard to keep something at 20. It's really easy to keep something at 0. All right. And then we just, hey, how do I solve PV equals nRT if we're looking for V? V is equal to? Very good. And N was what? What am I putting here? Yep. Oh, that's not an L. Liters, kilopascals per Kelvin mole. And then what's great, I'm just going to do that because we got more decimals than we need already. And on the bottom,
101.3.
and again, I'm just going to do that because we've got way more sig figs than we need. And what's that? So that's like 2.7. It's going to be 9. So we should be on the high 70s, low 80s, maybe even mid 80s. What are we looking at here?
77.
What is it, 77?
Yeah. Rounding.
Yeah, and what's our unit?
Liters of water.
Very good. Does that make sense? And was 2 sig figs what we were given? Yeah. Everyone see that? And all we did was multiply and divide, so 2 sig figs means 2 sig figs. There we go. Does this make sense? Is that reasonably okay? The truth is, this is actually much easier stoichiometry than the solution stuff. It's really, like, way easier. Because with the solution stuff, you have the fractions, right? Like moles per liter and blah, blah, blah. It gets confusing. This, straightforward. Very straightforward. So I want you to work your way through these questions. I'm here to help if you need help. Put your hand up. Don't be shy. Don't be a hero. Don't be a martyr. Put your hand up. Be like, hey, I need a little help. And then I'll come give you help. That's what I do. That's what I get paid to do. Yeah, you bet. Sorry? Do you want to just look it over? Oh, it's great. Let's take a look here. So here we're going.
I'm just seeing if it's right.
Oh, this is the one we just did. Oh,
Yeah.
No, this is. Oh, different.
Yeah, this is
okay. Yeah, different.
I'm just, let's just ask this then. Separated.
Oh, you're doing it all. Oh, okay. That's fine. So you start with grams per 2, and then you turn that to moles. Yeah. And then, that's your that's R. That's then RT over B. Beautiful. Yeah. If I were like superdimensional analyzing it, what I would probably do is just say, like I would probably just make these. You know what I mean? Like keep it in line. Just because sometimes too, one of the other nice things about dimensional analysis is you never get big long fractions, because now that we have decimals and stuff, it's not so bad. But on a calculator, doing big long fraction lines is, yeah, you know what I mean? Yeah. Whereas if you just do it, in fact, I would probably even just only put the last one there.
Yeah. In the end, it all
And then
makes
you just
sense.
multiply by that. Yeah, as long as there's no adding or subtracting, it doesn't. But that's great. That looks awesome. Well done. And then here, I mean, I'm assuming.
I didn't see that. It's all water. Because basically,
Yeah, those look great.
and that one is
You're doing great. Those look awesome. Yes, sir. We're ready for. Yep.
Is this getting marked?
Yeah.
Oh, okay, so you can't like check it over.
Oh my god, wait.
Okay, why?
I hate balancing questions.
Okay. Right. Five's around. Oh.
Just so metal.
Yeah. Yeah. I was writing too fast.
It's nice. The software I use, it's so funny. You just type in the name, you click a button, and I show you. It's so cool. I get excited.
I had a question. I did both just in case because I didn't know.
Butane 2-all.
Okay,
this is good. The only thing with an alcohol, this is 1, 2, 3, 4, so that's butane.
Yeah.
You have the alcohol on 2.
Oh.
The only thing with an alcohol is it's not a double bond to O, it's a,
single bond?
yeah, al is double bond to O, and then there'd be no H.
So just be
So that's just single bond OH.
okay.
Yep, that's
single
beautiful.
bond, okay.
But other than that, you're good. Yeah, so
Was
let
that for
me-
Butin 2-all?
Yeah.
There's 2 different pieces of software you can do it in. So one is just MoleView, which you guys also have access to.
Oh yeah,
which is nice.
yeah, I messed around with that before.
So you can be like, what is, I don't know, 2,3-dimethyl 4 propyl oct 1,2 diene
It's on Teams.
7 all.
Holy crap.
And if I did my naming right, oh, I screwed something up. Okay, well let's just make that 1-ene. Oh, because I couldn't do a 1,2 diene because it's got 2 methyl on it. I made something impossible. But this it'll do. Bam.
Wow.
And there it is.
Wait, is this on Teams or? how
Yeah,
does it-
this is called mole view,
Cool.
and it actually not only does it figure it out, it actually figures out something you don't need to figure out, but which shape it'll actually go. Like that, this will actually kind of bend around like that. You never need to know.
That's
that.
wild.
But isn't that cool?
Yeah,
So there's the 1-ene, and then there's the 2-methyl. See, it looks small because it's going down. There's the 3-methyl, so 2,3-dimethyl, and then there's the 4-propyl, so 1, 2, 3 propyl group, and then the main chain. And actually, this doesn't. Does this number them? I don't think so.
Doesn't that coffee taste better because it's free?
Always. Thank you very much. I really appreciate it. And I like it actually shows you what it looks like in 3 dimensions too,
That's
which
cool.
is pretty cool.
That's pretty sick.
So yeah, it's nice.
It's a cool program.
I don't use this for the things because it gets the angles so accurately.
Yeah,
It's actually
yeah.
less useful.
Yeah.
Like I don't want that overlapping and things like that.
See, you're the best teacher because like no other teacher would let me just go into.
Yeah, nobody would
Ain't gonna
say here. here's a
I'm pretty sure I didn't do that. Pretty confident.
Oh yeah.
Yeah,
That's right.
That
I
Yeah, I didn't.
yeah.
You didn't ask me. That's right. I just
went
wanted.
temporarily deaf for 5
Yeah.
minutes.
you guys are seniors, and you, I mean, you can do what you want. Seriously, right? You're in charge, so I don't have to worry about the safety concern of it. Or
Yeah.
that's all.
Yeah, for sure.
Because I'm 19. So.
That's right.
Oh, I went to the casino and $140.
I know you're
I
saying.
couldn't believe that, man. That's
Why?
so awesome.
I'm telling you, the trick now: run away.
Yeah, that's
Yeah,
run away.
that's
I go
the
there,
plan.
every
You
time
never
I
go again. You'll be the last
Yeah.
person to ever go there and win.
Every time I go to
Yeah,
the casino, I
real.
just put $5 in the machine, and if I lose it, I don't. I just leave. But if I win, I'll just.
I think
Yeah, but I was like, oh, maybe I'll just do it one more time.
the trick
I-
to
Maybe
I-
I'll win this time.
the trick to the casino to me, I don't go. I worked there, so I thought I'm never gonna go because it starts being way too easy, right? I'm there every day, so that's not smart. This is right, like this. This is how people start
you work
like.
there, you can't
This is how people start selling their children. So I thought not doing that, right? So I never went, but I always thought like the people who came in, and to them this is fun. I like it. Whatever I'm going in with, I'm expecting to lose, right?
same.
Like
100%.
right? Like and it's no different than, if you go to a hockey game, that's cost me $150. So if somebody else says, hey, what I really enjoy is playing blackjack, whatever.
Oh my god.
don't like blackjack.
I'm so good at blackjack.
But you know what I mean? Like
I don't
if,
like
if to you it's like this is a night of entertainment, I can have a good time,
Oh my god.
and that's fine.
Drinks are expensive.
Oh my god.
If you think you're gonna win, the only thing you can conceivably win at is the card games because there is a skill
there is-
element.
yeah, there is.
And unless you're, and here's the deal: you know if you're someone who can win at those. And if you're not sure, you're gonna lose. But that's fine. If it's a hobby to you and you're like, this is fun, I'm gonna lose this money, but I'm gonna have a good time. And then once in a while, hey, I have a little bit of money. That's nice.
Oh my god.
But if you go thinking, I'm gonna hit it big.
Oh no,
Yeah,
no.
you bound to lose. You jinx yourself. When I was a kid, I
I was thinking since I'm done,
Yeah.
I can run to the library and print out
That'd be great. Are you done that? Great. Start pile right where you are, and I'm gonna mark those before I leave.
About the different ways to get it. So
Yeah.
Would you be able to like continue with Stoic? Would
Yeah.
you be able to find the amount of liters through that? Because
Yeah, what you could do, because I mean, it's really doing the same thing.
Yeah.
But because this is n, here you're like, well, with n, then what else do you need here? R and T on top, and what do you need on the bottom? So what you could have done is, I'll rewrite this just a little smaller. You could have said 52 grams of O2, okay, times 1 mole of O2, for every 32 grams of O2, and then times 2 moles of H2O, for every 1 mole of O2. So I'm just writing exactly what you had here. And then here, instead of saying equals, now you know what you are at here now is n. So now keep going here. I'm like, okay, n, on top I need R, which is 8.314 liters kilopascals per Kelvin mole. And they can go right on the bottom. No number, but just, there you go. So that's R, right? R is 8.314 liters kilopascals per Kelvin mole.
So then that just acts as a 1?
Yeah. Yeah. And then you can put T in. And T is 200. T is what? 273 Kelvin, right? 0.15, but we only need 2 sig figs.
I memorized that number completely for the next day.
And then what do we need on the bottom?
P.
Pressure. And what's pressure? 101.3?
Yeah.
We'll say 101 kilopascals. And bam, there it is. And you just make sure everything cancels. Grams cancels with grams. Moles cancels with moles. Those moles cancel with those moles, right? And then liters cancels with liters doesn't cancel because that's what we're getting. Whoops. Kilopascals cancels with kilopascals. Kelvin cancels with Kelvin, and we're left with liters. So it's just doing the same thing. It just, you'd still have to do this, and you'd still kind of want to do that, and be like, okay, once I found this, I need those 3 things. It just means you don't have to press equals here. You can just keep carrying on. Some people like that. Some people hate it. It makes no difference to me. I teach it this way. But if you want to do that, go nuts.
Yeah, because I feel like that takes a little bit less time.
It does take less time, and it saves you having to press equals, write that down, come here, fill it out, right? I like this.
And it would still equal 77.
Yep. Oh, you'll get the exact same answer. Because you're doing the exact same thing. You're just not pausing in the middle.
I took these by mistake.
Oh, those are mine, yeah.
Yeah. Sorry.
So
No, don't be sorry. Hey, do you know what they sent me yesterday? Because I'm wondering if I didn't order it, but if nobody else was in, I'll keep it. It's kind of cool.
I was 4 days off. Ohio's not that far away. Yeah, we have a in the middle. Okay, so balance it. So three that.
Oh, your eyes are
Oh, we are going to see Canada? Yeah. I thought it was like customs, and I was like, what?
No, yeah.
Yeah, no, I was like, that's why I was confused.
I think you can. You only
Figured it out.
Yeah.
Oh, wait.
I can't go to the station. Like a build one. It's like a genuine one. Why? What are you looking at?
You just threw it over the brain at my feet and let it didn't explode. Really? Like, why, like,
No. Richard, it depends on the brain. Like, if you get like really high power,
Yeah, is this a limited reagent reaction?
I've blown up a whole trip.
Look, we're given two values, we have to do two.
One PSI away.
It's a limiting reagent.
Around.
Yeah.
Limiting
That's fine. Yeah.
That's true.
January now. We're doing ammonia gas. We're locating this gas. And trying to create It's history project. No, dude, you gotta be that one border patrol that like doesn't speak much. Oh yeah, yeah, no, because we're chilling.
Just wanted to say that I derived the present value formula successfully and I know what went wrong.
Okay, so you're not gonna give it to us, you're going to give us the tools to find it ourselves, right?
I think, yes.
Yeah?
No, the problem was in our A value at the start.
Right?
Yeah, well, let's might have to just go the extra mile, or I don't know, it's an extra reach out challenge. But the A value isn't just R, it was R divided by 1.5. Because our first term was 117 times 1.0025, all that stuff. That whole thing was A, not just the 117, it's just the regular payment. You know when you see it, just right now. And that made the denominator simplify a lot more.
Like the actual place. I went to Cheers, I think. It was sick. I also went to I want to go to Mel's.
Oh,
and yeah, I always man.
Dude, it's not available right now.
I got like halfway up.
I know it's sick, right? Like, I want to see where they're actually looking at.
Have you ever seen me mad?
A lot of situations. Oh damn. What is it? I don't think it's I want to find out why my soul normally good. Why is it I have to say, flat hand. Yeah, when I was like 9 years old, I don't like that one is great after my family.
My what? Dry hand? They're not even greasy.
I'm on 8.
Just get right high. Up.
Oh, I got 9 minutes.
Okay. You look, you go hard.
He was looking for like millimeters of mercury.
You're like, oh,
No. millimeters of mercury.
You know what? This is sometimes you fucking hit me in the face, hit me with the balloon, sit down, and do your fucking work.
Really? So wait, it's 760.
Wait, where did it go?
So it's 764.
Where's your Fitbit?
I was going to, but it was done because I only got out to like
Volume is unknown.
Yeah, the math.
Since it's PM,
Oh my god.
Oh, I have to balance it. Chlorine gas is 1C2H5. I think it's 1. So what volume is CO2?
I lost it.
3 liters.
So, let's see what caused that. Did you end up with like a negative grams? Because that's weird. All right, let's take a look. I mean, the answer is probably you just accidentally threw a negative sign in somewhere. Yeah, you just accidentally threw in negative 188. Ah, it's negative 188. Oh, you don't subtract. Not to go from Celsius to Kelvin. You add. That's all. But hey, listen, how nice that you made a mistake and you instantly knew it didn't make sense. Right? That means you're doing it right. Are you all done?
Yeah.
Fantastic.
I have a question.
Mm-hmm.
For this part, you said this was all good, but then again, for first person.
Yeah, so no me, no.
Yeah, you said you were describing what the reaction did, not what you.
That's right. So the reason I say I am okay with saying we did this, I did this, but you still want to think.
As if it's like a formal paper.
It's more formal, which again, there are some teachers, some professors will say you may not use the first person at all. That's fine. Mm-hmm. Some will say you may. That's me. Both are acceptable. But even then, when you're writing formally, always think, what's the most direct way to say what I'm saying? Yeah. So if you are saying that hydrogen reacted with oxygen to make water, you didn't do anything. You know, in your materials and methods, you can say, we did this, we did that, this happened, that happened. But when you're talking about your conclusion, what was the chemistry of it? I see it, thank you. What was the chemistry of it? You didn't do the chemistry, the chemicals did the chemistry. So don't say we react, our oxygen and our, or we get this. Because I think what you'd said something was like, we get this.
Yeah,
right?
yeah.
And it's like, well, you don't get anything. Like the reaction happens and that's produced. And like, you can still write really short, quick declarative sentences. I'm not looking for faux deep science writing. Like I'm not looking for you to try to sound fancy. That's not what I'm saying here. But I am okay with I and we in key places. But when you're describing the chemistry, just describe the chemistry. Does that make sense?
Yeah.
Okay.
When you said you were describing what the reaction did, what you did here, so like.
Yeah. So let's see. So like.
Highlighted this part.
Yeah. So instead of saying like we got this, we should have gotten based on our stoichiometry. Instead, what you should be saying is that like this much was produced, or the reaction yielded this much, or whatever, and it should have yielded that much. Because again, if you take the language literally, and I know this is just how we speak, but if you take the language literally, it's implying that like you made this much when you should have made that much, when really you didn't make anything. You know what I mean? Like you didn't sit there and craft it, like the reaction happened. So it's a small point, but it's just learning. It's just learning voice. It's learning when to deploy more casual language, and when you have to be a bit more objective in your language. And this is a case where you need to be a bit more objective in your language. And that'll come with practice. Overall, your writing's really good. It's nice.
I also added this part, so I added in like a chemical, because you told me I did forget like the chemical reaction part, and then
You didn't forget it. Just
like
forget it.
so I said it was a synthesis reaction. So I said that, saved that. I was gonna add on to this. So I just did this morning in English. So
Yeah, that's a good start. It looks good. I would say like a synthesis reaction which follow the general form A plus B yields AB. You know what I mean? Like make that a full sentence, but that's good.
that part, yeah.
Yeah, and I would say like the burning of the magnesium gives the magnesium oxygen to react with. I wouldn't say. Rather, I would say burning is
supplying.
not even burning is reacting with oxygen. That's what burning is, right? So you could say when magnesium burns, it reacts with oxygen to produce magnesium. I gotta say, you look good.
Thank you.
It's good. It's good luck. Did you make that? See, you thought you were making a boat, but really, making a hat.
What's that word?
Yamaka?
Yamaka.
Yeah, I think would a ramaka be like a yarmulke made from ramen noodles?
Yeah.
Would it be sacrilegious to consume a yama? I think it would.
That sounds that does sound great.
I think you should open a kosher restaurant and everything on the menu should be a pun. Like you could order the ramaka and it's a yarmulke shaped ramen noodle. That's kosher, and so it's okay to eat, you know?
Okay. Make this happen.
Alright, I'm in.
With your knowledge of
I know that. I can run a restaurant. I can run a restaurant.
Okay.
The only thing I was ever any good at in my life.
That bottle was
You're a good chemistry teacher.
It reminds me of those shots that they have at bars. They flip it down.
It's true.
It's like
I used
instead
to
of
hate
saying
when people did bombs. It's like, this is obnoxious. It's fine with like 19-year-olds too, because you're like, all right, this is how people that age are supposed to behave. So it's like 32-year-olds, you're like, all right, you know what? You have moved on to a new stage in your life. It's called the not drinking this way stage. Anyway.
Oh my god. So guess what? Before Christmas, my savings account had almost $4,000.
Hey, wow.
Okay,
Look at
no,
you.
no.
Well, that's good.
No, but look
What
I
did you
did.
say? Oh no! Oh no! Oh well. Did you get some real nice stuff? Or did you blow it on
I
crap?
did, because I got my dad airplanes.
That's
I got
nice.
my mom suitcase big bag.
This is nice. This is loving. Extravagant.
A bit
It's
too much.
extravagant, yes.
I'm happy myself.
Yeah, what'd you get the boy?
I got him like 4 pairs of sweatpants.
Holy would
A
you?
bunch of just like little like stuff.
Wow, cute.
And then like a
That's nice. That's good. Sounds like you did well. You did good. But yeah, you gotta get saving. Get saving. Well, you'll get that back, I'm sure. Take that right here, my friend. Thank you.
I went to the library and said I couldn't print.
So now I gotta.
Then I went to 162 and I couldn't
Find water.
That is super annoying. That's okay. You can email it to me, and I will print it.
I emailed it to you.
Okay, I'll find it. This weekend I'm doing another big marking spree. I'll find it. No worries. Don't worry about printing it. I got it. Take it easy, kid. Have a good one.
Okay, so instead of I said before I said, oh, we got 82.5%, and instead I worded that like the 82.5% means that 82.5 of the true value was obtained, which was 0.